Namaskar, I'm Parth. Today we'll start binary morphological operations. If you haven't seen the previous video of binarization by Otsu's thresholding method, then please check that video before starting this. In this video, I'll show you erosion and dilation operations by manual functions. You can check here, this is our original image and this is the eroded image with the structuring element of a row matrix. One row and 5 columns, and the center pixel was the third pixel. So you can see the outputs of erosion and dilation, which also matches with the built-in functions. You can check also that. Okay, so let's start. Before starting, please subscribe to the channel if you haven't yet. Help us expanding our audience. Thank you. Okay, let's start with erosion first. This is the input image I have taken. This is the structuring element, and here we will place the values of output pixels one by one. So as you can see, this is 5x5 image and our kernel is of 3x3. So if we do not pad our input image, then we will have the output of 3x3 pixels, because if you place a kernel here, then you can see the first center pixel will be this. If we move forward, then it will be this. So our central pixels can be only at these locations. So the output will be of 3x3 matrix. Now the condition for erosion is we have to compare our structuring element or our kernel with the window where we are placing this kernel. Suppose we are placing at this 3x3, and if you see, this is black pixel and this is also black pixel, so it is matching. It is also no, this is not matching, this is matching, and this is also matching. So there are 3 pixels and these 2 also, so 5 pixels are matching and the rest are not matching, so it's a partial match. If it is erosion and we are getting a partial match, then the output will be 0. Okay, now we'll move our structuring element and we'll check for this. Here you can see it's again a partial match, so the output will be 0. Now if you see in this image or at this position, our kernel is exactly matching the image window, so the output will be 1. Now if we move further, this is a partial match, so once again output will be 0. Once again it's a partial match, output will be 0. In this case it's completely not matching, so again output is 0. Let's move forward. Still it's not matching, and once again at this position it is completely matching, so we'll give output 1. So this is input image and output image with this structuring element, and it is also necessary to specify center pixel. If the center pixel would be not in exact center and somewhere else, then the output would differ. If you have not followed well, then once again I'll show you the process. It's partial match, it's partial match, now it's complete match, still partial match, partial match, completely not matching. So it's like contradicting. There are all black, here are all white pixels, so it will be still 0 output. It's partial match, and here once again it matches completely, so the output will be 1. So that's all for erosion. Now let's see dilation. I have used the same image and same kernel or structuring element. The only change in condition for dilation is if it's a partial match, the output will be 1. Unlike erosion, in erosion if partial match, then the output was 0. But in dilation, the output is 1. So we'll start As you can see, it's partial match. This pixel is matching, this is matching, this, this and this. So total 1 2 3 4 5 pixels are matching. So it's a partial match, so the output will be 1 this time. It's once again partial match, so output will be 1. Now it's complete match, so output will be 1. Now it's a partial match because corner pixels is both are matching and the central pixel is matching. So again 1. This time also it's partial match, but at this location it's completely unmatching. As you can see, every pixel is contradicting. Here this is a row of white, where in kernel it is black. In the middle it is black, where in kernel it is white. So there will be black pixel or zero output. And then again in all other conditions it's a partial match, and in this condition it's complete match. So output will be 1. So in dilation, you can see the difference in both outputs. This was the erosion and this was the dilation. Erosion breaks the bond. You can see in this erosion's output there was a bond between this row and this row. That bond has been broken, and in dilation there exists this bond, and even in fact you can see this bond is now of 2 layers. Previously it was of 1 layer. Now this 1 layer is increased, if you can see, and this boundary values are not present. So dilation basically creates bond between 2 objects, and in contradiction erosion breaks these bonds of white pixels in the image. I will go through the dilation once again. Not match, partial matching, it's complete matching, partial matching, partial matching, completely not matching. This is the only necessary condition in dilation. Okay, now let's start implementation in Matlab. Okay, I have created this template function which we use for the rest of our operations. Let me clear all. Okay, now let's start. First of all, we have to find the row and column of structuring element by given input location. So let's start. The first element which will give in location will be row, and the second will be of column, because if you have seen the animation, structuring elements center pixel can be anywhere in the pixel. It's not necessary that it should be in the geographic center or that kind of center. It can be anywhere. So first user will specify that what is my structuring element, and then he will also specify that this is the point of my center in the structuring element or in the kernel. Okay, now we will define the size of structuring element, which is simple. Okay, now in this method, which actually Matlab inbuilt also applies, there we paired arrays. We paired 0 values in the image so that input image and output image size match, because in various applications matching size is very necessary. Okay, so the output will be of the same size of input, so we'll simply write E is equals to size of A. Okay, now we have to pad rows and columns. Now let me once again go to that animation. Now if you can see, this is our central pixel, so we placed it like this. In any condition we have to place it like this, but this was our central pixel, so the output was reduced to 3 cross 3. Now if this was our central pixel, suppose this black pixel, then you can imagine we can move from here, then we can also go to here, so it will be 3. Now we cannot go beyond this point. if this edge comes here, and we cannot go beyond that because there are only two values here, two pixels available. We need a third pixel to move, so we cannot move forward. So the output will be three columns, and we can move down to 1, 2, and 3. So once again it will be a 3 cross 3, but the output would be different. So that is the important thing. So if we need output in the same size as input, then we have to pad how much rows and columns that we can find by extreme conditions. See, if our central pixel is this, we are finding output for this pixel corresponding to this pixel. So there will be needed two more columns and two more rows, right? So we will find likewise how many rows or columns need to be padded. Okay, let's start. Okay, so the padding depends on the size of structuring element and how far the center is from the structuring element. So let me show you so you can easily understand. The required row padding is this much. Our center of the structuring element is suppose in the fifth row, and total rows in the structuring element are 10. Then if we place in the last row structuring element, then how many more will be required? Then we have to subtract that. So it's very easy, you can find it. In the same way we will find the padding required in column. There can be also some other different method, but this is easy to understand. Okay, now we will pad this much. Okay, so after padding, our new image will be a new. There is an inbuilt command pad arrays. Sorry, it's all small. We have to pad in a how much row and how much column we have calculated. Okay, and what we have to pad is necessary to specify. We have to pad 1 or we have to pad 0. So in the case of erosion, we will pad 1. We can also check by padding 0 what happens. Okay, now we'll run the loop. By running the loop, we will find extract each window, and then we'll compare it with our structuring element, and according to any of these condition, we will place output. Okay. So these are our loop variables I and j. We will extract the window. So we'll name it pin. So in this variable, we will extract from our padded image. We will extract from I to I plus S1. S1 is the number of rows in our structuring element. So we have to start from the first pixel, and we have to extract number of rows as in structuring element. But Matlab starts with 1. So we have to take, if in structuring element there are 3 rows, then we have to take 1, 2 and 3 rows. And what will be the output here? 1, 2, 1 plus 3, so 4. So but we need 1 to 1 plus 3. So as Matlab starts indexing from 1, we have to do a -1 here. Same in j, we will go from j to j plus s of 2. S of 2 is the number of columns, and same in row, we have to reduce 1, means we have to do -1 to adjust the indexing of Matlab. Okay, now we have the window. So now we will create a temporary variable which will store the values of equals means if our window is matching to the structuring element or not. So we'll write, okay, we will test it actually. See, 1 2 3 4 5 and 6. This is our say window, and our kernel is 5 2 3 6 5 4. Okay, so let me just, so you can see both. Now if we do a equal to k, then we will get the values where this is matching. So these are the 3 points, 1 1 1. So you can check, there are the matching points. So in this temporary variable which you created, there will be stored that which pixels are matching and which are not matching. So in case of erosion, if all pixels are matching, then and then only we will assign the output 1, otherwise the output will be obviously 0. So if any value from temp is equal to 0, so if any variable is 0, then we will do nothing, because already, okay, here we have made a mistake. It will be zeros of size of a. So already we have given all values 0 in that image. So if anyone is 0 in matching our window size and kernel, then we have to do nothing. But if it's not matching, then we'll write 1 to that location. Fine. So this is complete match, and this is partial or complete unmatch. So that's it. Now we will try running it and find if we have made any mistake and there are errors. So I'll take input image as cameraman. Sorry. Okay, let me show you that image. This is a gray image, and currently here we are talking about binary morphological operations. So we'll convert this in binary. You can also use the function which we have created in the previous video. So this is the image. Now suppose we have to find the column of black pixels. There are how many, if we get the pixels where there are black pixels in some say number, like 7 pixels are black in a column. So first we'll invert the image so that this black pixel is I'm talking about turns white. Okay, now we will find the column of white pixels which are existing, like number of 10. Okay, so we will give structuring element as ones of say 15 rows and 1 column. Okay, now we have to also decide location of our central pixel. So this is our structuring element. Then if this structure is matched anywhere in the image, then where you have to place the 1 in the first location or in the middle anywhere or somewhere else. So I will place it here. So location will be first row and first column. Okay, now we have our input image. Now we have structuring element and the location of our center. So we will find E as the output image erosion is our function's name, where we have to give input image A, structuring element, and location of output pixel. Line 14, column 1. Okay, we have not ended this to for loops. Okay. Oh, now there is no error. Let me also just write in this function to show our output image. Okay, let's run the function again. So now the output will also be displayed. Now you can see these are the values where there were series of, or I can say columns of 15 white pixels. Let me also show you the input image. See, this was the input image, and see here also there were some 15 pixels. So there are some white pixels. In this sticks or in this tripod also there are some number of more than number of 15 pixels. So there are also some white pixels here, and these are white pixels. That is erosion, and we will do same thing in dilation, but the only change will be the condition. So let me copy this whole code. We will name it dilation. Same output will be there. We will just name it D for the sake of understanding that it's dilation. Okay, then the only change will be, first of all we change the name, so we'll change them here also. Now if it's a partial or complete match, then we have to place 1. So now we'll write here 1. So if any pixel is matching partial match or complete match, if any pixel is matching, now this will become complete unmatched, and this is completely matching, because here we have written any temporary variable equal to 1. So if any variable or any value is 1 in that variable, then it means either it's a partial match or a complete match. So we'll write this statement there, and in this else condition we'll do nothing. It's just sake of writing this else condition, otherwise we can remove that condition also. So there are no other changes except this so-called formalities. Okay, so that's it. The dilation is also ready. We'll just save it and let's try. We will use the same structuring element, same input image. Let's see. We'll name it D. Okay. She made a mistake. I said it's formality, as I said. Okay, this is the dilated image. As earlier said, dilation makes bond, erosion breaks bond. So this is the example you can see. Let me also show you eroded image. See, this was the input image, this figure 3. We used the structuring element of a column array of 15, you can see here. So in erosion, bonds were broken. It was connected here, it was connected here, this was broken. And in dilation, you can see this, the connectivity is increased. So in morphological operations, where we need to disconnect some two objects, or if two objects are very near to each other and there is a silver lining, you can say, between two objects, then it can be removed by erosion. And to create the boundaries or to merge boundaries, dilation is used. Thank you for watching the video. Please like, share and subscribe the channel and help us reaching more and more audience. Thank you.